Okay, let us continue the second part of today's class. Okay, please go to the slides of chapter 2 and go to page 23. Okay, we have just talked about this reference, Kwasinski and Liu, 2008. Okay. This is a paper written by Kwasinski and KJR Liu. Okay. The title is Source Channel Cooperation Trade-offs for Adaptive Coded Communications Transactions Papers, which is published in IEEE Transactions on Wireless Communications in 2008. Okay, here I put a hyperlink here, okay, which is the blue one. Okay, you can click on this hyperlink, and your browser should automatically open this web page, and you can click the PDF button. Okay, here. Like this. Okay, and you can click this download. Click this arrow to download this paper. Okay, like this. Okay, let us go back to the slides. Okay, let us go back to page 23. The source encoding distortion DIS depends on the source encoding rate XIS, which is subject to the limit of the channel throughput RIS. Okay. For conciseness, okay, what is conciseness? Let us look at the handout. Okay, let us look the handout. Okay, page 23, problem 1. What is conciseness? Solution: short and clear, expressing what needs to be said without unnecessary words. Okay, this is the meaning of conciseness. Let us go back to the slides. Okay, for conciseness of discussion, we can adopt a synthetic. Okay, what is synthetic? Let us look at the handout. Okay. Problem 2. What is synthetic? Solution: synthetic products are made from artificial substances, often copying a natural product. Okay. Okay, synthetic Gaussian source. Okay, what is a Gaussian source? Let us look at the handout. Okay, problem 3. What is a Gaussian source? Okay, solution: a Gaussian source is a source whose output is a sequence of statistically independent, identically distributed Gaussian random variables. Okay, that is dots U-1, U0, U1 dots, each with the probability density QU is equal to 1 over the square root of 2 pi a, and times the exponential of minus u squared over 2a. Okay, I think you have learned the course probability. Okay, when you were an undergraduate student. Okay, So I think you know that this is the probability density function of a Gaussian random variable with zero mean and variance A. Okay. So let us go back to the slides. Okay, a synthetic Gaussian source. So we can also call it an artificial Gaussian source that provides the worst distortion case for all possible source sample statistics. Okay, what is the meaning of this sentence? Let us look at the handout. Okay, problem 4. A synthetic Gaussian source provides the worst distortion case for all possible source sample statistics. What does this sentence mean? Source. Okay, solution. Okay, sorry, not source, solution. If we assume that x is a Gaussian random variable with variance sigma x squared, and if we assume that successive samples of the signal x are stochastically independent, okay, that is independent in probability, or equivalently, the source is memoryless, okay, or the signal is uncorrelated, okay, because the successive source is independent. So source 1, okay, at time 1 and time 0, okay, the two samples does not have any relation, okay, so they are independent and without memory, okay. That is, the sample at time 1 do not remember what is the value of sample at time 0, okay, or the signal is uncorrelated, okay, because we know that the independent implies the uncorrelated. Okay, we find the following analytical expression for the rate distortion function. Okay, we will explain what is the rate distortion function in problem, okay, let me see, in problem 5. Okay, so the rate distortion function R of D is equal to 1 second times log 2 of sigma x squared over D. If 0 is smaller than or equal to D, and D is smaller than or equal to sigma x squared, okay, where D is the distortion. And R of D is equal to 0 if D is greater than sigma x squared. Figure 10 shows what this function looks like. Okay, please see figure 10. Okay, figure 10 is the rate distortion function R of D of a Gaussian source with variance sigma x squared. Okay, you can see that the x-axis is D over sigma x squared. That is the distortion divided by the variance of x. And the y-axis is R of D. That is the relationship between the rate and the distortion. So it is called the rate distortion function. Okay, we can see that when D over sigma x squared increases from 0 to 1, the rate distortion function R of D, okay, decreases, okay, from about this value, okay, to 0. And on this interval, the rate distortion function is a convex function. Okay. And on the interval 1 to 2, the rate distortion function is equal to 0. Okay. Rate distortion theory. Okay, we will see what is rate distortion theory later. Tell us that no compression system exists that performs outside the gray area. Okay, so that is for any compression system, the relationship between R and D, that is between the rate and distortion, the pair is always lies in this gray area. Okay, we'll never go to this white area. Okay. The closer a practical compression system is to the red lower bound, the better its performance. Okay, that is, for example, if I had a point 1, 2 here. Okay, 1, 2 here. Okay, we call this the first point, and the second point is here. Okay, and then we know that the second point has a better performance than the first point does. As a general rule, this bound can only be attained by increasing the coding block length parameter. Nevertheless, even at unit block lengths, one can often find good scalar quantizers that operate at distances from the rate distortion function that are practically relevant. Okay. Okay, what is the coding block length? Okay. For example, if I had a bit now, okay, then I encode this bit into a block, a coding block, and the coding block has n bits. Then I call the coding block length is equal to n. Okay, and what is the quantizer? Okay, the quantizer is a, okay, you can see that is a device or a block or a object that can do the quantization. Okay, this rate distortion function holds only for Gaussian memoryless sources. It is known that the Gaussian source is the most difficult source to encode. For a given mean square error, it requires the greatest number of bits. The performance of a practical compression system working on, say, images may well be below the R of D lower bound shown. Okay, that is, okay, a practical compression system, because its source is not the Gaussian source. So for a practical compression system, okay, its performance may below the red lower upper bound. That is, it will fall in this white region. Okay. Okay, next, let us see problem 5. What is a rate distortion function? Okay. Please pay attention, because the definition of the rate distortion function is very difficult to understand, okay, in my opinion. Okay, solution. The functions that relate the rate and distortion are found as the solution of the following minimization problem. Okay, we can see that first is inf. Okay, inf. Okay, what is inf? Okay, let me show you. Okay, what is inf? Okay, so inf is the abbreviation of infima. Okay, of a subset S or a partially ordered set P is a greatest element in P that is less than or equal to all elements of S, if such an element exists. Okay, let us see some example. Okay, for infima, the infimum of the set of numbers 2, 3, 4 is 2. The number 1 is a lower bound. Okay, that is 1 is is smaller than 2, 3, and 4, but not the greatest lower bound, and hence not the infima. Okay, because the greatest lower bound is 2. More generally, if a set has a smallest element, then the smallest element is the infimum of the set. In this case, it is also called the minimum of the set. Okay, next, infimum of 1, 2, 3, etc. is equal to 1. That is, the infimum of the set of all natural numbers, that is, the all positive integers, is equal to 1. And the infimum of this set, okay, where x belongs to R. Okay, what is R? Okay, the R is the set that contains all real numbers. Okay, and 0 is smaller than x, x is smaller than 1. Okay, is equal to 0. Okay, you can see that 0 is smaller than all the elements in this set, and among all the lower bound, 0 is the largest one. Okay, and you can observe that 0 is not in this set, so the infimum of a set does not necessarily fall in this set. Okay, let us see infimum of this set. Okay, x is in Q, where Q is the set contains all the rational numbers. Okay, and x to the power of 3 is greater than 2. Okay, then we know that this infima is equal to the cubic root of 2. Okay, because the cubic root of 2 is greater than all the elements in this set, and the cubic root of 2 is the greatest one. That is, it is the greatest lower bound of this set. Okay, so again we can see that the cubic root of 2 is not a rational number. So again, the infimum of a set does not necessarily fall in this set. Okay, and next, the infimum of minus 1 to the to the power of n plus 1 over n, where n is equal to 1, 2, 3, etc. is equal to minus 1. Okay, why? Okay, let us see the blackboard. Okay. Because I do not have a blackboard now, so I use the Microsoft Word instead. Okay, let us see that this. Okay. Problem 1. Find infima of the minus 1 to the power of n plus 1 over n, where n is equal to 1, 2, 3, etc. Okay. Let me, it should not be italic. Okay, so let us see this problem. Okay, let us see the solution. Okay, here I only provide an intuitive solution. Okay, please note that this solution is not a rigorous, in mathematics. For when n is equal to 1. Then the minus. Let me copy this. This should be the 1 over n. Sorry. 1 over n. Like this. And it should be text. Then the minus 1 to the power of n plus 1 over n. This n should be italic. Is equal to minus 1 to the power of n plus 1 over 1. This is 1. And this is equal to minus 1 plus 1, and is equal to 0. Then when let me copy this. When n is equal to 2, let us see. The minus 1 to the power of n plus 1 over n is equal to 2. Minus 1 to the power of 2 plus 1 over 2. So it is equal to 1 plus 1 over 2, and it is equal to 3 over 2. Let us continue. Again, when n is equal to 3, then minus 1 to the power of n plus 1 over n is equal to minus 1 to the power of 3 plus 1 over 3. and this is equal to minus 1. Okay, it is 25 minutes. Let us take a break.